Okay, now that we're starting talking about solutions, we're going to talk about some of the ways they behave. One of the things that makes solutions different from pure solvents is something called colligative properties. Colligative properties have a definition that they are properties of a solvent that change when you add a solute. We are going to talk about primarily two of them. One is boiling point elevation, and the other is freezing point depression. What happens when you add a solute to a solvent, the boiling point and the freezing point change. So if you are looking at water, water normally boils at 100 degrees C, and it freezes at 0 degrees C. But what we're going to do is when we add a solute like salt or sugar, these numbers actually change. Boiling point goes up, freezing point goes down, and the magnitude of that change, how big the change is, depends on how many solute particles you have present in the solvent, and we will talk about that when we get to calculations. Okay, the first thing we do need to talk about is vapor pressure, because that is very much related to these colligative properties. So at any temperature, water will evaporate into a gas. It's called a vapor. You may be familiar with this if you've had a glass of water on your nightstand and you leave it there for a few days. You might notice that the volume of water has gone down even without drinking it. It evaporates. It's called a vapor. And as the temperature increases, the amount of water that evaporates also increases. And eventually you get to a point where the pressure of the evaporated liquid water, it's called vapor pressure, equals the external pressure on the liquid. At that point, the liquid will boil. That's what boiling point is when the vapor pressure equals the external pressure on the liquid. And as a matter of fact, that's why in Colorado, we can't get water to boil at 100 degrees C. Our temperature is typically around 97. And the reason why is because our external pressure is lower. And that means that the vapor pressure of the liquid doesn't have to go as high, so the temperature doesn't have to go as high. The temperature is actually lower. And it's not possible to make water boil at 100 degrees in Colorado, unless you have a pressure cooker or something. Okay, so let's talk about boiling point elevation. Okay, boiling point elevation is due to the fact that when you add a solute to water, it decreases the ability of the water to evaporate, which means the vapor pressure goes down. And if the vapor pressure goes down, it has to have more heat added to it in order for the vapor pressure to equal that external pressure, because the vapor pressure went down and it's got to get to whatever that external pressure is. So it needs more heat to make it evaporate more to get to that point. And boiling point goes up. Okay, we're going to do a calculation with it. We are going to approximate on the calculation here. We're not going to do the actual calculation. It's not very hard, but we're just going to stick with the approximation. There's the equation. Please put it in your notes. The little triangle means change in. So delta TB means the change in the boiling point, how much the boiling point changes by. And then K is a constant, and it's determined by whatever solvent you're using. And this is the value for water. We'll give it to you. M is the molarity. You should be familiar with this. And then I is a little bit tricky. I is the expected value of the number of ions in aqueous solution, and I'll show you how to figure that out when we get to those kind of problems. Freezing point depression is a similar idea. You add a solute to water, it lowers the vapor pressure. In order to freeze the solution, you have to take away more heat from the solution to make it freeze. So the freezing point of the solution is actually lower than the pure solvent. And freezing point decreases. And this is why we put salt on snowy or icy roads in the winter. It lowers the freezing point of the solution. So water normally freezes at 0 degrees Celsius. So that would be snow and ice. So if the air temperature is -2 degrees Celsius, all the ice and the snow are going to freeze. But when you throw some salt on there, what happens is it changes that freezing point and it drops it down to maybe -5 degrees C. Well, if it freezes at -5 and the air temperature is -2, it's going to turn into a liquid. It's going to melt, okay? The other way it is used is when we make ice cream. If you've ever made ice cream at home, what you do is you take cream and sugar and vanilla and you put it in a plastic bag, and then you get a bigger plastic bag and you fill it with ice water and rock salt. And what that does is the rock salt lowers the freezing point way down and the cream will freeze. That's how you make ice cream. Okay, the way you calculate it, we're going to approximate this one as well. The equation is very similar. The delta with the T and the F is the change in the freezing point. K is a constant and it's determined by the solvent. For water, it's 1.86. M is the molarity. Again, you should know that. And then I is also the number of ions. So let's do a few practice problems. Okay, the biggest thing you want to do is pay attention to the number of ions. Since colligative properties depend only on the number of particles you have present, the ionic compounds, things like salt, have a bigger effect because they dissociate in water and produce multiple ions. So if you have an ionic substance in water, I is the number of ions. If it's a non-electrolyte or if it's not in water, I is 1. Okay, so let's do this one. It says calculate the change in the freezing point and the boiling point of 25 grams of salt in 100 milliliters of water. Assume complete dissociation and that water normally boils at 100 and freezes at 0. So delta TF and delta TB. The calculations are very similar. First thing is I. Well, if this is NaCl and I put NaCl in water, it's going to break apart into ions made out of sodium and chloride. Go back. That means the number of ions I get is 2. Okay, for both. The constant for freezing is 1.86 degrees Celsius over molarity. The constant for boiling is 0.51 degrees Celsius over molarity. So what I need now is I need the molarity. Well, if I have 25 grams of NaCl, just like we've been doing earlier, you want to change from grams to moles. You get 0.427 moles. To find molarity, you take the moles and you divide by the liters of the water, 0.100. And you get a molarity of 4.27. That number goes here, and that number goes here. Okay, so the change in the freezing point, multiplying these all out, molarities cancel out, and you're left with 15.9 degrees C. Same thing here, molarities cancel out, multiply, you get 4.35 degrees C. And so what this is telling you is how much it changes by. If I asked for the new freezing point, what I would recognize is that water normally freezes at 0, and it's going to drop by 15 degrees. So it normally, since it normally freezes at 0, the new freezing point would be negative 15.9 degrees. And if normally boils at 100, boiling point goes up. So I'm going to add the boiling point. I get 104.35. Didn't ask for that in the problem, but that is potentially going to be a question. Okay, so calculate the new freezing point and the new boiling point. So here's where it's going to come in. 50 grams of calcium chloride and 100 milliliters of water. Okay, so again, delta TF and delta TB. First thing you need to recognize is that calcium chloride turns into calcium ion and 2 chloride ions. That means my ions are 3. Now, I don't want you to get the idea that it's always the number of atoms. it's the number of ions, and I'll show you some that are a little bit different. The constant for boiling is 0.51. Constant for freezing is 1.86. So what I need is I need the molarity. If I have 50 grams of CaCl2, 1 mole is 111.1. Get 0.45 moles, divide by 0.1 liters, 4.5. So when you multiply this out, you get 25.1 degrees C is the change, and 6.9 degrees C is the change. But they want the new freezing point and the new boiling point. For water, it normally freezes at 0. It's going to drop by 25.1 degrees C. That's pretty drastic. And the new boiling point starts at 100, but it's going to add 6.9. Okay. All right, so now let's try this one. So the boiling point of the solution, that means we're looking for the new boiling point. Delta TB is how much it's going to change by. Now this is a non-electrolyte. If it's a non-electrolyte, I automatically equals 1. The constant is 0.51, and what I need is the molarity. So that's 0.433 moles of the solute over 0.15 liters of solution, which means the molarity is 2.89. Put that in here. And the change of the boiling point is going to be 1.47 degrees C. So the new boiling point, water normally boils at 100, and I'm going to add 1.47. Okay. Next one. Again, I have this, and it's being dissolved in something called benzene. Well, benzene's not water. If it's not water, I equals 1. So to do this, the new freezing point, delta TF, I is 1. I have a new constant because it's not water anymore, 5.12. I still need the molarity. So when I divide out the moles, I have 0.292. Divide by the liters, and my molarity is 1.95. Put it into the equation and solve, and you get a changing in the freezing point of 10 degrees. So the new freezing point is based on the old freezing point of 6, and subtract the change means it will now freeze at -4. Okay, the only other kind of thing you might run into would be multiple choice questions dealing with this. Okay, and so we're talking about the lowest freezing point in water, delta TF equals I, M, and KF. Since they're in water, the KFs are all the same. They're all going to have a value of 1.86. To put this in to the equation to find the biggest change in the freezing point, well, if it's a non-electrolyte, I equals 1. So the equation here would be 1 for the ions, 1 molarity, and 1.86. For this one, I is 2. So you have 2 times 0.5 times 1.86. And this one, also complete ionization, ionizate equals 3 times 0.5 times 1.86. So the bigger the delta TF is, the lower the freezing point's going to be. That would be your answer. The next question says, which would have the lowest boiling point in water? Well, the lowest boiling point in the water is going to have the one that is the smallest change in the boiling point, and that would be A. And then the last question you guys should be prepared to discuss when we come to class is why we add salt to ice to make ice cream. Okay, I have a couple of links for you if you're interested. This link will it's an article from Scientific American, and it'll tell you how to make ice cream using freezing point depression. And then this is a video on it.